Unfortunately, our second speaker could not make it today, so we have a recorded video for this session. The talk will be Understanding Deep Learning Performance Through an Examination of Test Set Difficulty, and John Lalor recorded the video for us.
Good afternoon, everyone. My name is John Lalor, and I'm a PhD student at the University of Massachusetts Amherst. Today, I'm going to present our paper, Understanding Deep Learning Performance Through an Examination of Test Set Difficulty, a psychometric case study. This is joint work with my co-authors Hao, Chenden, and Ham. Before I start, I want to say how disappointed I am that I can't present this work in person. I hope all goes well with the video, and thank you very much to Emma for setting everything up for me in Brussels. If anyone has any questions about this presentation, please feel free to email me. To start, let's look at the examples on this slide. These were taken from NLP datasets for natural language inference and sentiment analysis, respectively. If they were used in a test set for some deep learning model, each would carry equal weight when calculating test set accuracy and therefore determining model performance. But if we look closely, we can see that certain examples are easier than others. For example, there is a difference between the two negative sentiment examples, with the first being very negative and the second being closer to neutral. Having some notion of the difficulty of each example would help us analyze the performance of models trained on these tasks. We could determine whether model performance is affected by difficulty and how that relationship changes as models are trained with more and more data. In this paper, we conduct a case study using psychometrics to investigate how both training set size and the difficulty of specific examples affect model performance. We utilize item response theory from psychometrics, a framework for estimating latent characteristics of test set questions, called items, and latent ability parameters of test takers who provide answers to the test questions. IRT is typically used in standardized tests like the GRE and GMAT, and in prior work we applied it to building a new test set for the natural language inference task. A common IRT model, and the model we consider in this work, is the three-parameter logistic model. For a given individual J and a given item I, the probability that individual J will answer item I correctly is a function of individual J's latent ability theta and item I's latent discriminatory, difficulty, and guessing parameters. This plot shows what is known as the item characteristic curve for an item where the discriminatory parameter A is 1, the difficulty parameter B is 0, and the guessing parameter C is 0.25. A represents the slope at the steepest point of the curve. B represents the level of ability at which an individual has a 50% chance of answering an item correctly, in this case at ability level 0, and C represents the lower asymptote of the curve. For this example, the steeper slope indicates that the item is more discriminatory at a narrow range of ability. The lower difficulty parameter means that this item is easier, since now an individual with ability of -1 has a 50% chance of getting it right, and the lower guessing parameter means that individuals at very low levels of ability are less likely to answer this question correctly. So, how do we learn these latent item and individual parameters? Starting with P, we also have Q, which is just 1 minus P, and represents the probability that individual J will answer item I incorrectly. Now, the likelihood function for a set of individuals' responses to a set of items is shown here, where Yij is equal to 1 if individual J answers item I correctly, and 0 if they do not. To learn the item and individual parameters typically involves marginal maximum likelihood using an expectation maximization algorithm. In our prior work, we built a test set for natural language inference using IRT. I'll go through the steps at a high level, but I encourage you to look at that paper for more details. First, we selected a sample of items from the SNLI dataset and obtained 1,000 new labels for each of the items from crowd workers on Amazon Mechanical Turk. That way, we had enough response patterns to fit good IRT models. The next step was to fit an IRT model for each NLI label to create a test of ability to correctly identify entailment, for example. This involves an iterative process where certain items are removed from the test set due to things such as bad item fit. Finally, with our test sets built, we used a pre-trained deep neural network to take these tests and use the model outputs to estimate latent ability for each of the tasks. In this work, we once again look at the SNLI dataset and use the pre-trained IRT models from our prior work. We also look at sentiment analysis, specifically the Stanford Sentiment Tree Bank. For sentiment analysis, we selected a sample of about 130 items and repeated the IRT model fitting procedure described earlier. Going back to the examples we started with, the difficulty parameters in the right column are a result of the IRT model fitting process. We can see that certain items are easier than others. For example, the first negative sentiment item is much easier than the second because it is so negative. Now that we know the difficulty of our items, we can conduct our experiment to determine if item difficulty and training set size impact deep neural network model performance. For our experiments, we looked at 3 neural network models. First, we used the LSTM model provided with the original SNLI dataset. Second, we used a convolutional neural network architecture that had been applied effectively to a number of NLP tasks. Finally, we used a Neuro-Semantic Encoder model, which is a memory-augmented neural network that performs well on both the NLI and sentiment analysis tasks. To conduct our experiment, we trained each model with a subset of training data for each task. We started with a few hundred training examples and incrementally added randomly sampled training data until the models were trained with the entire training set. For each training set size, once the model was trained, we administered our IRT tests and recorded the model output for each item. With these outputs, we learned a logistic regression model to predict whether a model would correctly label an item, given the training set size and the item difficulty. This slide shows a contour plot of the results. The top row is the results for the NLI task, and the bottom row is the results for the sentiment analysis task. The x-axes are the training set sizes, the y-axes are the item difficulties, and the contours represent the odds that the model will label an item correctly. We'll zoom in on a few of the plots for a few more details. First, we'll look at the results for the LSTM model for both the NLI and the sentiment analysis tasks. We can observe 2 interesting patterns here. First, the easier items are easier than the harder items. This doesn't sound that interesting, but remember that these difficulty values were learned from human response patterns. So the fact that there is consistency between the model performance in terms of difficulty and a difficulty parameter learned from the humans is an interesting result. Second, we see that as more data is added to train the model, the easier items get even easier faster than the harder items. So not only are the easier items easier, but they are also easier to learn. These results are consistent across all of the NLI models, as well as the LSTM model for the sentiment analysis task. We did find some interesting patterns in the convolutional neural network and Neuro-Semantic Encoder models for the sentiment analysis task. For the easy items, the results are consistent with the other models. However, for the more difficult items, it turns out that the odds of labeling an item correctly actually decrease as the training set size increases. So these models are learning patterns for easy items at the expense of performance on the harder items. On the surface, this isn't necessarily good or bad, but having these difficulty parameters means that this is something that can be observed and understood before a model is put into production. So, to wrap up, in our IRT case study, we've learned a few things. First, that easy items are easy for these deep learning models. Again, at first that doesn't sound surprising, but remember that the difficulty was determined by human data. Second, model performance on the easy items improves more quickly than performance on the hard items as more data is added. This result may be useful when determining whether to obtain more data to train a model or looking into different architectures. You'll need more data to improve performance on these harder items if that's what you're looking for. Finally, the combination of task, model, and item all matter when evaluating performance. Certain models may behave differently for the most difficult items based on patterns learned during training. With that, I'd like to thank everyone for their time. Before I conclude, I want to say thanks again to Emma for her help in getting this presentation to you, and I encourage all of you to attend her best paper talk later this afternoon. Again, if anyone has any questions, feel free to email me. The response pattern data we use for these experiments will be available online. Finally, I'm currently on the academic job market and would love to talk with you about positions at your university. Thank you very much for your time and attention.
Okay, so as far as I know, there are no authors present, so we won't be able to, unfortunately, ask any questions, but you have the contact information there. Aaron, if you want to come up and set up for the next talk.